So far in the topic of enthalpy changes, we looked at a number of different enthalpy changes. So we looked at enthalpy combustion, enthalpy of neutralization when we did calorimetry. We looked at enthalpy of formation and a generic enthalpy change, which is enthalpy of reaction, which covers any reaction basically, and it's the enthalpy change for a given equation. So we're going to look at how we can compare different values by using the idea of standard conditions, because if I measure any particular enthalpy change for a reaction like combustion here, so if I burn 1 mole of carbon at 25 degrees C, I get enthalpy combustion of carbon. If I do it at 35 degrees C, I'll get a different value experimentally. So in order to be able to compare different reactions, we need to make sure all these values that we're comparing with are done at the same conditions, and we call these standard conditions. So that's what we're going to look at next. So as we just said, if we measure the enthalpy change of a reaction, whether it's neutralization or whether it's combustion, etc., at different conditions, we're going to get different values. They can be slightly different. So in order to have a fair comparison between different reactions or enthalpy changes of different reactions, we must make sure these values were taken at the same conditions, and we use what we call standard conditions, which is 25 degrees C and 1 atmospheric pressure, or an atmosphere. So 25 degrees C is 298 Kelvin, and 1 atmospheric pressure is about 101 kilo or 1000 pascals or Newton per meter squared, because 1 pascal is the same as 1 Newton per meter squared. Knowing this, then we can adjust some of these definitions of enthalpy changes for standard conditions. So the enthalpy change of reaction was defined as enthalpy change when the number of moles of reactants in an equation reacts to form the products. So that's any written down equation we're given, we can have enthalpy change provided for. If I have the standard enthalpy of change of reaction, that would mean it's the enthalpy change when the number of moles of reactants in the equation reacts to form the products under standard conditions, which is 25 degrees C and 1 atmospheric pressure. Standard enthalpy change of combustion then would be the enthalpy change when 1 mole of a substance undergoes complete combustion in oxygen under standard conditions, which is 25 degrees C and 1 atmospheric pressure. Standard enthalpy formation or standard enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states at 25 degrees C, 1 atmosphere. So what we mean by in their standard state is that if we look at enthalpy change of formation of water, water is formed from its elements hydrogen and oxygen. The standard state of hydrogen is a gas, and the standard state of oxygen is a gas. The standard state of water is liquid, because those are the states of matter at 25 degrees C and 1 atmospheric pressure. You notice that I've put the symbol here to show that these are standard enthalpy changes rather than just enthalpy changes. So this symbol here, which is a circle with a line across it, represents standard enthalpy changes or standard conditions. So lastly, the standard enthalpy change of neutralization is the enthalpy change when 1 mole of water is formed from the reaction of an acid and alkali under standard conditions. I've been saying for a while in these enthalpy change videos that we need to be able to write equations to represent different enthalpy changes. So if I were to write the enthalpy change of formation of glucose, I need to balance it for 1 mole of glucose, because by definition, enthalpy formation is the enthalpy change when 1 mole of a substance is formed from its elements. So if I want to write the equation to represent enthalpy of formation but under standard conditions, or the standard enthalpy of formation, I must make sure that we have the correct state symbols to show the substances in their standard states. So in the next video, we're going to look at Hess cycles and Hess's law. And in order to draw the correct cycles and get the calculation correct, we must be able to write these equations to represent different enthalpy changes. Otherwise, we're going to get the drawing of the cycles wrong, which is the most common mistake people make. The calculation themselves are not very difficult. What students find difficult is they draw the cycles incorrectly because they don't understand how the cycles are constructed. So the way I teach it is to show you how to construct those cycles rather than just tell you a shorthand way of doing it, which lots of teachers do. So I may do it slightly different to some of the teachers, but it's really worthwhile doing it so you understand why the cycles look like they do, rather than just learn where the arrows just point to by rote. So in the next video, we're going to look at Hess cycles and Hess's law and how to construct cycles, knowing how to write equations for these enthalpy changes that we've been covering in the past couple of videos, and using those cycles to calculate unknown values of enthalpy changes if we know the other values in the cycle.